Okay, so these are surface integrals. All right. Definition. 1461 surface integral. We're going to let g of xyz be a continuous function defined on a surface S. Then the surface integral of g on S is double integral over S g of xyz ds. So g is kind of like your density function. Okay? Surface integrals can be used to measure a variety of quantities beyond mass. If g measures the static charge density at a point, then the surface integral will compute the total static charge of a sheet. So maybe you want to know what the static charge of some object is or whatever, that outside surface. If g measures the amount of fluid passing through a screen, it's represented by S at a point, then the surface integral gives the total amount of fluid going through that whole screen. So let's do an example here. I want to find the mass of a thin sheet modeled by the plane 2x plus y plus z equals 3 over the triangular region of the xy plane bounded by the coordinate axes. And the line y equal 2 minus 2x. With a density function delta xyz equal to x squared plus 5y plus z, where all distances are measured in centimeters and density is given in grams per centimeter squared. Oh, fun. All right. So we've got a plane, like a sheet of paper in space, okay? And we want to find the mass of this sheet of paper, this piece of metal, whatever it is, okay? First thing I'm going to do is graph it. All right, so x, z, y. Okay, triangular region in the xy plane. So xy plane, bound by the axes, so x-axis and the y-axis, right? And then y equal 2 minus 2x. So we're at 2 on the y-axis, and then we're going down. So like this. Okay. Maybe it goes to right here. And where do we cross the x-axis at? X equal 1. Okay. So 0, and 1, and then I want to parameterize this little triangle area here. And if I graph this, if x and y are 0, then z is equal to 3. So it should look something along these lines here. So maybe this is the plane. Okay. Remember, it's projecting like we're looking up from that triangle down low. Instead of looking at that whole infinite plane, we're looking at that, just a triangle portion of that plane. All right? So how would I parameterize this? It might help us to redraw this in a little bit more familiar way that we're used to looking at it. So x goes from 0 to 1, and y goes from 0 to 2. Y'all follow what I'm saying here? Okay. So how would I do a u and a v here?
Well, the u could just be the x.
Okay, u could be x, and so that means that we're going to have u between what and what?
Oh, 0 and 1.
0 and 1, good. Okay, u can be x. Now what about v?
That would also need to be between 0 and 1 because you're scaling, I guess. Well.
Okay, so v would be between 0 and 1. So if v is equal to 1, what do I want the line to look like?
2 minus 2x.
Okay,
Or 2 minus 2.
so the y here, so I have x equal to u and have y. Right now, like if I just did y, I'd have 2 minus 2x, right? But that would be when v was equal to 1, right? If v was equal to 0, I would want this horizontal line here, and it makes up all the pieces in between from here to here, right? So just add that v in and set it between 0 and 1 to parameterize. Okay?
I got a question.
Yes.
If we decided to put the v with the 2x, would it just be the same thing except it's coming from the top point and spreading out?
I'm sorry, say that again.
So you see how it's going like this? It's breaking that way.
Yeah.
If you move the v with the 2x, would it just be like this? It would always start at 2.
I guess I don't understand what you mean to move the v with the 2x. Like,
So, let me pick that up.
yeah.
I just gonna take a perspective, I guess. So if you had y equals 2 minus
2x.
vx.
Okay.
If you put it right there, it would do this instead. Would that work? Or would there be some kind of problem with that?
Well, okay, let's just try one. Okay, if you don't, so you're saying you're just doing 2 minus 2 vx, basically?
Yeah.
Okay. So like if you had at v equal to 1, I would agree. V equal to 1 works. But what is v equal to 0 going to do? That's just going to give you y equals 2. Okay? Which I guess if it's at a single point, what if we did v equal to 1/2? V equal to 1/2. This would be
Oh, I see
2
what's
minus x.
happening. It's going
so-
this way. It's not going.
Yeah,
the way I
so
thought it
so
would. Okay.
it's not exactly. It would be more parameterizing outside of it.
Yeah, I see.
So yeah, that's the way I think about it is if I multiply the whole function by a number, what that does is it shrinks it. It'll push it down. And so like if v is half, then it's going to be half the heights, quarter of the heights, third of the heights, all all those values between the full height all the way down to flat. So that's what pushes it down. So, what is x equal to? X is your u, okay? So, that y part becomes v times 2 minus 2u. Okay. So let's parameterize this thing. So R of UV is U, comma, V times 2 minus 2U, comma, and what's the last component?
2u plus v 2 minus 2u. Oh, wait, no. Z equals.
Okay, look, it's, so what is, do we have Z? We got Z, it's up there in the sentence, right?
Yeah, we don't have it solved for it.
But we don't have it solved, do we? So right now, it's 2x plus y plus z equals 3. So I want z equals what? 3 minus 2x minus y. Okay? And what is x? That's u minus what? V 2 minus 2u. Right? Okay. Yeah, fun stuff. So 3 minus 2u minus 2v plus 2uv. Okay. So what do we want to do now?
Well, now we need to calculate the magnitude. We need to find
The derivatives.
with
So let's-
respect to U and V.
Yep. Let's do RU. So that's 1. And then what? Be minus 2v. Is that right? What's the derivative? That's 0. That's negative 2. Negative 2 times v. Negative 2v. What's the derivative with respect to u over here?
-2
Plus
2V.
2v. Okay. Now RV. So what's the derivative with respect to v here?
0.
0. Second one,
2 minus 2U.
it'd be 2 minus 2u. Good. Okay. The last one,
-2 plus 2U.
good. Okay. Now this one's going to be a little bit better for us. RU cross RV. I, J, K, I, J. So that's 1 minus 2v minus 2 plus 2v, 1 minus 2v, 0 minus 2, or sorry, that'd be 2 minus 2u, minus 2 plus 2u, 0 minus 2, or sorry, dang it, did it again, 2 minus 2u. Okay. So boom, boom, boom. So that's 0k. And then, oh dang, gotta fold that thing. Minus 4 plus 4v plus 4u minus 4uv. Okay, that's for the i's. Then the last one, minus 2 plus 2u for the j's. Okay, now if I go over on the other side, that's 4v minus 4uv. That's for the i's. And then I have 0 for the j's. And then 2 minus 2u for the k's. Okay, so so that's going to be 4 minus 4v minus 4u plus 4uv minus 4uv plus 4v. So those cancel, so I get 4 minus 4u for the I component. And then j is going to be, that's a 0, so that's going to be 2 minus 2u. And k is going to be 2 minus 2u, because that's 0 there. Did I get that? Son of a gun. Got it. All right. So now we need to do the magnitude, RU cross RV. So take the square root, 4 minus 4u squared, plus 2 minus 2u squared, plus 2 minus 2u squared. Okay. I think I could factor. What if I pulled,
You pull 2 of it.
could I pull a 4 out? No, pull a 2 out. So 2 squared pulled out. So it's 2 minus 2. So how many 2 minus 2u's do I have?
3.
I got 3 of them, don't I? No, well, this is 4 here, and that's 1, and that's 1, so that's 6, huh?
But and if you pull out the factor, you can square root it, right? And then bring down
Yeah.
the square root.
Yeah, so this thing is gonna get me. Wait a second. That's 4, 6.
Wouldn't that be the square root of 2? No.
No, I think this is right. This is 4. So that 4 and 1 makes 6. So there's 6, and then 2 minus 2 root. I'm sorry, minus 2u squared. So I got a square root of 6. This thing right here, the square root of the square, is 2 minus 2u, right? So I could write it as 2 square root 6, 1 minus u if I wanted to. But either way,
So pull out that first 2 though, wouldn't that be the square root of 2? Because if you took out a factor of 2, then to take it out of the,
yeah, so when you take out a factor, how many are there?
it would be a 2 inside of the
Here, let me write it out for you. it is a little confusing.
I mean, I get it, but it's just like.
Well,
The
look, 4 minus 4u
Mhm.
times 4 minus 4u, right? That's the thing squared. So I pull a 2 out here. Ah, dang it. See, I can't even write it. And then pull another 2 out there. So that's why it's 4. Makes sense?
Yeah.
Yeah, it's not, I'm not acting like it's easy. It's not easy to do. It's kind of tricky. So, so then you got 4 of those, but then I have another one here and another one here. So 1, 2, and 4 makes 6 of those.
Yeah, I get all
And
that.
when I square root this, the 6 doesn't simplify, but this thing becomes just 2 minus 2u, because square root of the square is just the absolute value. And u is between 0 and 1, so we can drop the absolute values. So we get this thing right here, right? All that to get that ugly thing there. So mass is equal to the double integral over the surface dm, which is the double integral over the region the density function evaluated at r of uv cross or times the magnitude of ru cross rv dA. And so this becomes the integral from 0 to 1 of, okay, what is our density function? The density function was x squared plus 5y plus z. So I use x, which is u, so I do u squared, and then plus 5y. What the smoke? Where's my y? Okay, it'd be 5. Sorry, I should have wrote this better. 5v 2 minus 2u plus 3 minus 2u minus v times 2 minus 2u. Okay. Simplify that. So this last piece here, this is that piece we just found, the 2 square root 6, 1 minus u du dv. This thing simplifies. 0 to 1, 0 to 1. U squared minus 8uv minus 2u plus 8v plus 3. Multiplied by 2 square root 6, 1 minus u du dv. Multiply all that stuff out. See, I could pull a 2 square root 6 out. 0 to 1, 0 to 1. Minus u cubed plus 8u squared v plus 3u squared minus 16uv minus 5v, or sorry, 5u plus 8v plus 3 du dv. Integrate with respect to u first. So that's minus u to the 4th over 4. It's 8 over 3 u cubed v plus u cubed minus 8 u squared v minus 5 over 2 u squared plus 8 vu plus 3u from 0 to 1. Two square root 6, 0 to 1, 8/3 v plus 5/4 dv. A lot of math, algebra, get that junk. Right. Then if you integrate this thing, you get 31 square root 6 over 6 grams. Whatever the heck that is. Well, that's one page. I don't know how I thought I was going to get through all this.
How many more pages is it?
3. All right. Let a surface S lie within a vector field F. We want to measure how much of the vector field passes across S. That is the flux of F across surface S. So we want the amount of F orthogonal to the surface, so perpendicular with the surface. So what we really want is F dot the normal vector. This is the unit vector that's normal to the surface at the point. Okay? To get this vector, it's equal to derivative with respect to u cross the derivative with respect to v. Remember, the cross product of two vectors gets you your thumb pointing up, right? You remember this in the right-hand rule? So it's perpendicular, and if those two derivative vectors are tangent with the plane, then that cross product is going to be normal. But then we need to make it a unit vector, so I divide by its magnitude. RU cross RV. So what does the flux equal? The flux is the double integral over the surface of F dot N ds, which is a double integral over the region of F dot RU cross RV over the magnitude of RU cross RV. But then what is ds? Remember what ds was? It's the magnitude of RU cross RV dA. And so what happens that's nice here is these two complicated things go away. They cancel each other, right? That's the cool thing about this Little trick here. Double integral over the region of f dot ru cross rv dA. It's a lot easier. And this works for S that's orientable. So normal vectors must vary continuously across a surface. Okay. So we got a definition here. 14.6.2. Flux over a surface. Okay. Flux over a surface. Basically, we're taking what we did in section 14.4 and we're putting it into 3 dimensions now. All right, so we're just upping it a dimension. So I'm going to let F be a vector field with continuous components defined on an orientable surface S with normal vector in. The flux of F across S is double integral of S F dot n ds. If S, the surface, is parameterized by R of UV, which is smooth on its domain R, then the flux is equal to the double integral over the region F of R of UV dot RU cross RV dA. If S is closed, N should point to the outside. Okay? N should point to the outside. Orientable, once you get it, the outside is the outside. One thing that's kind of like a weird thing, it's called, have y'all ever heard of a Mobius band? You know what I'm talking about? Alright, I'm not gonna waste my time with that then. Alright. If you don't know what I'm talking about, then don't worry about it. Basically, it's a band, and it doesn't always, it doesn't point to the normal won't point. As you travel around it, you'll end up traveling around both sides. It's kind of weird. Doesn't even make sense. But best way I can describe it to you. Okay. So would you agree? Let me put this. We have one side that has squiggles on it and one side that does not, right? So if I loop it around like this, the squiggle is always on the inside. So normal would always be on the outside. That's orientable. But a Mobius band takes this and twists it.
I've seen this.
And so now, dang it, this doesn't work.
It's kind of like a spiraling ring.
So it's gonna work with the longer one. So this is all, so you can kind of see the squiggle here. Well, if I make one twist to it and connect it, now what happens is, even though I'm always on the outs, so this is a Mobius band, right? So I'm on the outside, I'm on the outside, I'm on the outside, but as I follow, now all of a sudden when I get back around, now I'm on the inside. And so it's not orientable because the outside doesn't always stay outside. If you traverse the path long enough, you get on the inside of it. That's a Mobius band. So there's a little trick. You watch 100 videos on Mobius bands if you want to. All right, so positive flux means that we move. So we're moving from back side to front side of the surface. Negative flux means we're moving from the front side to back side of the surface S. Okay? So here's the example. All right. Let S be the plane from the previous example. That plane was 2x plus y plus z equals 3 on the triangular region. So once again, R of uv was u comma v times 2 minus u 2u, and then 3 minus 2u minus v 2 minus 2u. And this is for u on 0 to 1 and v on 0 to 1. Let the vector field F be defined by 1 comma x comma negative y. And I want to find the flux across the surface. Okay, so we want to find the flux across the surface. So remember our formula. Flux is equal to double integral S F dot N ds, which is what? Double integral on the region, F composed of R of UV dot RU cross RV dA. Okay, that's my formula, right? First thing we do with all these questions, write down the formula. Get you a couple points at least. Okay. Then, what do we need? Well, for starters, we already have this thing. It's right here, isn't it? Yeah? So, can I plug in to get F of that thing? What is F? Okay. So, F is always 1 in the first component. What is it in the second component? An X. And what does X equal? U. And then what is it in a Y component? Or is the Z the last part? Is a negative Y. So I take the negative of this Y part here. So that's negative V 2 minus 2U. Are you guys okay with where that came from? Are we good with this first part here? What about this second part? How do we get this? RU cross RV. How do you get that? Y'all talk me through it.
We have to take the partials of R and then cross them.
So take the derivative with respect to what?
U and then
U, and then take the derivative with respect to V, and then do the cross product. Have we already done this?
Yes.
We already got it. So let's just get, so look back at your notes. RU cross RV. What did we get?
uh, 4 minus 4U, and then 2 minus 2U, 2 minus 2U.
4 minus 4U. 2 minus 2U. 2 minus 2U. Good. Okay. So, to get the flux, I've got to dot those two things together. Now, the region R is what? Region R is bounded on what variables? U and V. 0 to 1. Good. 0 to 1 for both of them. So 1 comma U comma, I'm going to go ahead and might as well just multiply it out, huh? So minus 2V plus 2UV dotted with 4 minus 4U, 2 minus 2U, 2 minus 2U, and then du dv. Thinking about making this one a test question. All right, fair enough. Tell you which one it's going to be in this section. Did y'all hear me? Okay. All right. So dot this up. So first and first, so 0 to 1, 0 to 1. So that's 4 minus 4u plus, what's the next one? U times 2 minus 2u is what?
Just 2U minus 2U squared.
U squared. Okay. Plus the last one. multiply these two pieces. That's, oh man,
Minus 4v.
minus 4v plus 4uv, right? And then plus 4uv minus 4u squared v and du dv. Does anything cancel? Hopefully, my gosh. Does something cancel?
No.
The u's
Oh, yeah, wait. You can combine.
we can combine at least.
That's it.
Is that it?
You
Yeah.
can combine the first two parts,
Um,
except for the,
We can do what's what.
oh crap. No, we can combine this. That's 8, right? I think that's it. Son of a gun. 4 minus 2u minus 4v minus 2u squared plus 8uv minus 4u squared v du dv. Okay, so yeah, not exactly the best. And we just learned that we can't do double integrals in this stupid calculator. So we're actually going to have to do this one. Okay. All right. For u minus u squared minus 4uv minus 2/3 u cubed plus 4u squared v minus 4/3 u cubed v 0 to 1. Okay. So plug in 1 for your u's, so you get 4 minus 1 minus 4v minus 2/3 plus 4v minus 4/3 v 0 to 1 dv. Okay. 4 minus 1 is 3 minus 2/3. So 3 minus 2/3 is 2 and 1/3, right? That's 6, that's 7/3. And then how much v's? Those v's cancel, so you're minus 4/3 v dv. So 7/3 v minus 2/3 v squared 0 to 1. So that's 7/3 minus 2/3. It's 5/3. How about that? Okay. So if that's a test question, what am I testing you over? What I'm really testing you over is everything we've done in this class, right? Okay. So this test question, this is a good, this actually, I think I am gonna make this is probably gonna be a test question, okay? So this right here, you gotta take a derivative with respect to u. You gotta take a derivative with respect to v. And you gotta do a cross product. So that's like 3 different sections in Cal 3, okay? Dot product's another section, so that's 4 sections. Then this f composed of this thing, that parameterization, so that takes care of the parameterization. So that'd be my parameterization question. Y'all follow me here? So like I'm not gonna have, you know how we had 14.5 was like all about parameterizing? So this is gonna be my parameterization. You're gonna have to parameterize in here, okay? So I'm knocking out like 2 sections in one question. Y'all good with that? Okay? Instead of making 20 points, this is just a 10-point question, okay? So, all right, it's a lot, it's a lot. So that's 5 sections. Then we got a double integral. Okay, that's a whole nother section. That's So we're covering this one problem gets 6 sections. So this really is a cumulative test, isn't it? Even though we're only doing it over chapter 14, we got stuff from 11, 12, 13 in here. All right? And 14. So this test, I could just make the whole test this one question, huh? Yeah, you want to do that?
Yeah.
Just do that? All right. So that's the end of that question there. Oh man. And now I got 2 more pages. I got 23 minutes to do the rest and we're halfway. So halfway through the notes on this one. So yeah, I know, right? I'm trying to think what I want to do here. Oh man. It's bad.
Do we have to take the exam on Monday, or could it be pushed to Wednesday and just use Monday?
No, we have to do it Monday because of the testing schedule. Yeah, I know. Because there's only 4 or 5 of us, but I have to keep the exam schedule. Okay. We'll do this problem. All right. This one's going to take a whole page. Okay. Let S1 be the unit disk in the XY plane. And let S2 be the paraboloid. Z equals 1 minus x squared minus y squared. For z greater than or equal to 0. Okay. So what does this look like in 3 dimensions? Right here? Yeah. So we got the unit circle on the XY plane, right? And the paraboloid. So we'll call that surface S2. And the bottom, that circle, the unit circle, S1. Y'all good with that? So that's my surface. Okay? The boundary for S1 and S2 is x squared plus y squared equals 1. That's the unit circle. That's the boundary. I'm going to let F1 be 0, 0, 1. So it's a vector field that pushes up 1 unit everywhere. And I'm going to let F2 be the vector field that's 0, 0, z. So the only difference is now the z component tells you how high up to go. Okay? So as it goes up higher, the vector field pushes harder in the higher in the z direction. So using normal vectors for each surface that point upward. Find the flux of each field across each surface. So first thing we got to do is we've got to parameterize. Okay? So we got to parameterize here. So let's parameterize the bottom, that unit circle first. Okay? So parameterize S1, the unit circle. Now, how do I parameterize the unit circle? What would I do?
V cosine U, V sine U.
V cosine U, comma, V sine U. That's perfect. That's exactly how you do it. And so U would be what? From what to what? 0 to 2 pi. And V would be from what to what? 0 to 1. Good. Okay. That's not too hard. Now, I need a normal vector. N1. How do I get a normal vector? RU cross RV. Right? And then when I cross it, my thumb points outside the surface. Okay? Which this one is going to point down. Right? Y'all follow that? Points down. Okay? I mean, I don't even have to go through all this math, and I know it's going to be pointing down, but we'll go through it, and hopefully it works out. Okay? So, what is RU? So this is kind of like a practice for our test question, because it's kind of the same thing. We've got to calculate RU and RV. So what's RU? Okay, so negative V sine U, and then V cosine U. Good. What is RV? Okay, cosine U, sine U. Good. Okay. Now, I kind of screwed this one up because you don't do a cross product of a two-dimensional vector. What is the y? What is the z value always on that unit disk? 0, right? On the xy plane, z is 0. So I forgot. Put my 0 here. Sorry about that. Okay. But I realized it when I was about to do the cross product. So let's do u cross v. So I, j, k, I, j. Negative v sine u, v cosine u, 0. Negative v sine u, v cosine u. Cosine u, sine u, 0. Cosine u, sine u. Multiply. For the k component, I have v cosine squared u. For the I component, I have 0. For the j component, I have 0. Okay. For the I component, I get 0. For the j component, I get 0. And for the k component, I get negative v sine squared u. All right, so I get 0, 0, and then negative v cosine squared u minus v sine squared u. What does this equal?
Factor out negative v, which is 1, so you just negative 1.
So you get 0, 0, and then negative v, right? Yeah, if I factor the negative v out, I get cosine squared plus sine squared, which gets you 1. Okay. All right, does that make sense that it points straight down? That's normal to it, right? Okay. Trying to figure out why I chose the positive one. We want positive z component. Why do I want a positive z component?
The normal vectors point upwards.
Well, I'm trying to figure out, because I thought we wanted a normal vector pointing outwards.
Because you said if we know that the normal vector is going to point downwards, right?
Yeah.
So if we want a normal vector that points upwards, then we have to take the negative of the normal vector.
Yeah,
And
I'm
then-
just, did I say that? Oh, golly. Using normal vectors for each surface that point upward. It's written in the problem. Okay. I was like, why the heck did I want it? All right, that makes sense. I wrote it in the problem. So in the problem, it says that they want it to point upwards, okay? Ours points downwards, so we need to fix it. So if it points downwards, the normal vector points downwards. Well, what is the other normal vector points? And remember, it's the negative of the direction. You flip the cross spot. If I have u cross v, this is equal to the negative of v cross u. Y'all remember that? And it just, your thumb goes from this way to this way. You just switch the u and the v positions, okay? So all we got to do is the negative of this thing here. So this is 0, 0, positive v. So that's my normal vector that I want. Because the problem specifically says they want it to point in the upward direction. If they didn't say that, then you just point outward, all right? So the flux across S1 is equal to the double integral over the surface 1, F1 dot N1 ds, which is a double integral over the region of, well, what is F1? F1 is this integral here, 0, 0, 1, dotted with 0, 0, v. And then dA, okay? Now, our region goes from what to what? 0 to 2 pi and 0 to 1. Okay? If I dot product this thing, what am I left with? What is the dot product of that?
Just v.
It's just v, isn't it? And du, dv. So that'd be uv 0 to 2 pi. So that's just 2 pi v integral 0 to 1 dv. So that's v squared pi 0 to 1 which gets you pi. Okay? So the flux across that surface, the bottom surface is pi. All right? So it's flowing through. If you imagine it like a filter, it flows through the bottom at pi units. Okay, that flux. Now, for the other surface, the bullet part, the paraboloid, what was the paraboloid? Z equals 1 minus x squared minus y squared. Okay? For z greater than or equal to 0. So that boundary is still the same as that unit circle, right? If I'm parameterizing the surface, okay, so that's still the v cosine u, v sine u, but my z value isn't always the disk, is it? It's not 0 anymore. What is it now? 1 minus what? What is it?
1 minus v squared cosine squared u
Mm-hmm. Minus
minus
v squared
squared
sine squared u. Good. Okay. It's good. Now, we can simplify. Sine squared and cosine squared make what? 1. So technically this becomes v cosine u, comma v sine u, comma 1 minus v squared. Okay, so that makes it a little bit easier. And this is the same parameterization for the limits of integration. Okay, the only difference is now instead of having a 0 here, it's 1 minus v squared. Okay, that's the difference. So I need to calculate RU and RV again. So more practice on calculating RU and RV. So RU is what?
negative v sine, wait, v sine u.
Sine U. And then V cosine U. And 0. And then RV. Cosine U. Sine U. Minus 2V. Okay. So then we got to do the cross product. R cross V. RU cross RV. Okay. So IJK. IJ. Minus V sine U. V cosine U. 0. Minus V sine U. V cosine U. Cosine U, sine U, minus 2V. Cosine U, sine U. So V cosine squared U for the K, then 0 for the I, then plus 2V squared sine U for the J. And then going this way, minus 2V squared cosine U, 0 Wait, dang it. I did that wrong. I think I did the J first. Okay. And then the K was. Wait, did I do
J would be 0.
did I do that right?
You did I first.
I did it right. Okay. That's what I get for second guessing. All right. It's there, and then there, and the last one is over here. And so that would be minus V sine squared U for K. All right. So minus V sine squared U. The I is minus 2 V squared cosine U. And J is 0. So minus V. And then sine squared and cosine squared make positive 1. Then minus 2, so that's for my K component. Then minus 2 V squared cosine U for the I. And then 2 V squared sine U for the J. So my vector, minus 2 V squared cosine U, minus 2 V squared sine U, and then minus V for the Y, or the Z part. Okay? So that's RU cross RV. All right? So now I would cross this to get the flux across S. So the flux across S2 is equal to a double integral across the surface of S2, F2 F1 dot into, okay, TS. What? Yeah, we're still, I just realized that, yeah, the second, which I'm not going to get to it unless y'all want to, but the second one, F2,
We would do the same things except just.
you do the same thing, you just replace 001 with 00Z, okay? But let's get through this and then I'll just touch it, okay? Region R, 001, dotted with that terrible thing. But the good thing about dotting something with 001, what happens to the first two things?
0.
They're gone. They gone, right? And so, you know what I didn't do? Same thing here.
We're across there the wrong.
I went the wrong way. So how do I make that go the right way?
Put this in.
Just make everything positive. So positive, positive, positive. So make everything positive and we're good. Okay? Because we want to flow in the upward direction. So we get double integral R of V dA. And what do we know? R goes from 0 to 1, 0 to 2 pi, V du dV,
It's the same as the last.
which is the exact same as the last one. So we don't even have to do that work, it's pi. These two results are equal and positive. Each are positive because both normal vectors are pointing in the positive z direction, as does F1. All right? F1, that flow is going up. 001 points up. As the field passes through each surface in the direction of their normal vectors, the flux measured is positive. So we can also intuitively understand why the results are equal. Let F1 represent the flow of air, and let each surface represent a filter. Since F1 is constant, okay, what is F1? F1 is 0, 0, 1. No matter where we are, it's just going up at a unit 1. Since F1 is constant and moving straight up, it makes sense that all the air passing through S1 also passes through S2. Y'all follow this? So think of this as like some filter. So even if that filter makes a cone, that all that air is going straight up, it goes straight up through the unit circle, the same amount as it does through that cone. Y'all follow that? So, because this thing is constant here. Okay?
That might go up, we would call that projected area.
Projected area.
So it's the same thing.
So it's calculates out to be the exact same calculation when you're looking at flux. Okay? Which is kind of crazy. All right, you would think that it would be more because there's more surface area, but it's not. Okay, it's the same. Okay? Now, let me just show you my notes here. So you don't need to write this out. Just watch it. Okay? I'll just talk about it. Okay. So if we treat the piecewise surfaces as one, we made sure each normal vector points outwards. Okay? S1 would have a flux. Now, when we calculated it, we were going up, right? But if we treat it we point it down, well, if we go down, instead of it being positive pi, it becomes what? A negative pi. Does that make sense? When we calculated that flux, we got pi, right? For the unit circle, but it was flowing upwards. Okay, so now we're pointing outwards, so that means we're going to point down, so in the opposite direction it's going to be negative, which implies the total flux across the closed object. Now the top one was what? It was pi, and if the bottom one is negative pi, then what is that total flux across? 0. Okay? So why was the flux the same? So the divergence, if you took the divergence of that vector field, which was 001, this is V2, right, or F2, right? So our original one was the constant 001. If I take the divergence of that, that gets me 0. The derivative with respect to x plus the derivative with respect to y plus the derivative with respect to z. That gets you 0. So the divergence is 0, so that's why the flux was the same across. Okay? So now instead of it having that, let's change it to where v for the last component instead of a constant 1. Okay? Well, I mean, when you calculate the divergence now, it's not going to be 0 anymore, is it? Okay? So let's do flux across S1. So this is F2. Okay, so what is F2? So wait a second. Oh, okay, here we go. So to get this 0, 0, 0, that's F2. We plugged in our original. Okay, so all that work that we did, if you plug in your R1, this thing right here, okay, if you plug that in to F2, you're going to get 0, 0, 0. All right, those first two components are 0. The last one for that first one is 0. You dot it, you get 0. Okay? The flux across S2, right? You do your whole song and dance, you plug that in, you get this thing here. Dot it with that, so you have 1 minus v squared times v, gets you v cubed minus. No, it doesn't. Why did I do the negative of that? That would be v minus v cubed. Huh. Yeah, whatever. It's just a negative. I don't know why it's not. Why I did that. That should be v minus v cubed. Okay. Whatever. So that's how that cookie crumbles. I don't know, I guess I goofed up on that last part here. But regardless, it's not the same. Measure of flux differs over S. The field F2 is 0, there's no flux. And over S2, the paraboloid part, the flux is positive. It's different because the divergence is not 0 this time. So, whoop-de-doo.